Chris Atkins, Associate Director of Mott MacDonald, and today I'll be explaining basically what goes wrong with structures and why materials fail. As was mentioned, my name is Chris Atkins. I work for Mott MacDonald in something called the Materials and Corrosion Engineering section, which looks at materials. It's kind of handy because everything's made of something, so it narrows down my field of expertise. This afternoon you're being talked about exotic things that sound like they shouldn't be made into fibres but are. Basalt, carbon fibre, glass fibre, all that kind of stuff. Most things generally aren't made out of this kind of stuff, they're made out of steel and concrete. So I'm here to cover the steel and concrete and what goes wrong and why things go wrong. First thing to know, concrete is a great material. Structurally it works, it's durable, it can last a long time, you get the impression that nothing really goes wrong with it. Wonderful stuff, but functionally it cracks. Structurally it has to, that's how it transfers load into the steel. We know bits can fall off because that's why I have a job. It can also be attacked by chemicals. We think of it as an inert lump, but to be honest, it's alkaline, and when you chuck acid stuff on anything alkaline, it reacts. There's a couple of other things that can happen too. And the commonest thing I have to deal with, we put steel in it to cope with the cracks, but the steel rusts. Right, to carry the loads in concrete, it cracks. A lot of the early reinforcement designs we have are basically there to control the size and spacing of the cracks. That's kind of what they're there for. Typical design code used to be make the cracks less than 0.4 millimetres in width. Wonderful. If you want a water retaining structure, you make the crack less than 0.2 millimetres width. The Euro codes have changed all that, so there's a whole range of other things you have to consider, but that kind of worked for a very long time. The other thing concrete does is crack where you don't want it to. We come across designs that have come up with spacings for joints that are rigorously applied, and we'll have the joint here, here and here, and then they get confused when it cracks somewhere else. You don't tell the concrete where it's going to crack, the concrete will crack where it's going to crack. So they might not happen where you expect them to happen. I'm a civil engineer. As a civil engineer, I'm really imaginative and come up with great ways of naming things. So first thing, plastic settlement cracking is cracking due to settlement that occurs in the plastic phase. Basically, concrete, before it's gone hard, is a pile of rocks and sand and stuff in water. If you shake it about too much or it's too sloppy, the rocks and sand and stuff settle down and you get cracks. That's plastic settlement. Also, when it's in its plastic phase, it's kind of watery. If you let it dry out too much, it shrinks. And because it's shrinkage that causes the cracks during the plastic phase, it's plastic shrinkage cracking. If you come across cracks on site on a fairly freshly poured piece of concrete, first thing to do, give it a light grit blasting, because then you'll actually realise the true extent of the cracks. If you can see one or two, there's probably hundreds of them. So before you set out fixing hundreds of cracks by a method you thought would be cheap and simple and just involve injecting one, grit blast it. Find out how many cracks there are. Early thermal cracking is cracking due to early thermal effects. Basically, concrete going hard, chemical reaction, gives off heat. So it gets hot and expands. Then it goes hard and cools. And as it cools, it shrinks. And as it shrinks, it gets tension in it. So you get cracks. And a lot of reinforcement designs are actually based on this. It's kind of handy when you come to fix a motorway pier, because it means, yes, you've got lots of corrosion, but structurally it's not that significant because we put a lot of steel in to cope with the fact that it was hot and then got cold. Long-term drying shrinkage is shrinkage that occurs over long term due to drying. Basically, stick concrete in an environment, it'll dry out and reach an equilibrium with the surrounding area. If the humidity around it is low, it'll shrink a bit more than the UK. Typically the cracks will be nice and evenly distributed due to all of these things because it happens uniformly over the structure. But if it's fixed in one place because there's a lift shaft there or there's a corner of a slab it's tied into, it's going to change it around a bit. This is a water retaining structure, undergoing its water test. Quite a big water retaining structure, there's a bloke. Obviously, if you own this water retaining structure and you're testing it, you're going to be mildly annoyed that there's a lot of water coming out the side of it. But the cracks are nice and evenly spaced, so they show up that it's a materials thing, it's universally shrinking. In this case, concrete occasionally does a very useful thing called autogeneous shrinkage. The cracks self-heal with a bit of time. We measured them all, they were all in requirements with the design code. The autogeneous shrinkage basically filled them up, and after a couple of months with water sat in it, it stopped leaking. Similar kind of thing, reservoir, nice evenly spaced cracks. The ones at the corners are diagonal because you've got a different restraint going on at the corners. So they're nice and sensible and vertical. And we were called in to say, why is this one kind of at an angle when all the rest are nice and straight? It's just because restraint, that's the way it's going to happen. On joints, this is a joint on a building in South Africa. That's the edge of the building, and that's the edge of the building. And the designers, in their infinite wisdom, decided we would put joints at a set centre across the entire building. And the building overall was, I think it was 210 metres, 0.15. So they divided it into nice 35 metre lumps. So they put a joint every 35 metres, which meant that the extra 0.15 theoretically is a free floating corner of the building and a free floating edge. It's not going to work like that. There's no way on earth that that is going to be a separate piece of concrete behaving independently to the rest of the building, and that joint is going to move 75 millimetres in 3 dimensions. So you need to have a bit of a think when you're doing things. In this particular structure, they had joints running up the middle of columns with reinforcement links going across the joints, and it's not going to move like that. So don't forget trying to design the joints to cope with the middle of a column suddenly moving 75 millimetres out, because that isn't going to happen. You need to have a bit of a think. Plastic settlement. Basically, concrete settles down when it's wet. You can spot where all the reinforcement is. Durability-wise, that might be a problem. This is a structure up in Scotland, in a water retaining structure, and you've got the same kind of thing. The bars are basically immediately underneath the cracks, which means the bars aren't in nice friendly concrete anymore. The bars are basically in the water that's collecting in the cracks. So they're probably going to give you a corrosion problem, and you need to do something about them. For chemical attack, it's either chemicals on the outside going in or chemicals on the inside kind of mucking up the concrete anyway. Concrete's alkaline, so acid attacks it. Concrete's got a load of calcium in it, so soft water attacks it. Soft water likes having more calcium in than it's got. The one we worry about for concrete in the ground is sulphate attack. Internally, civil engineering naming terms again, alkali aggregate reaction is a reaction between the alkali and the cement and the aggregate. Can be called alkali silica reaction if you've got silica aggregate. Can be called alkali carbonate reaction if you've got carbonate aggregate. Delayed Ettringite formation is a delay in the formation of Ettringite. So again, we're showing our commitment to innovative names. That is a rag that I dangled into a tank of sewage and scraped up the side of the wall. That's universal indicator, measures pH between 1 and 14. That little red bit there says the wall of that tank was at pH 1. If you lived next to a sewage treatment works and it smelled, historically you just accepted that was because you lived next to a sewage treatment works. In more recent times, you complained to the owners of the sewage treatment works, who are very into customer care these days, and they come along and they put a lid on it. That's a GRP lid. What that does, the smell in sewage is hydrogen sulfide. That happens when you digest sewage. If you put a lid on the tank, the hydrogen sulfide collects on the underside of the lid. There you get oxygen-reducing, sulfur-oxidizing bacteria that react with this hydrogen sulfide and turn it into sulfuric acid of about pH 1. Net result, you lose about 10 millimetres of concrete a year. Durability-wise, that's fairly bad. In this case, it was on 110 mil wall thickness, so basically they get to the steel in about 3 years, get through the entire wall in about 10, because they put a lid on it to please the neighbours. Estoril, interceptor sewer. If you were a public works engineer in Portugal in the 60s, you basically looked at your local population, thought 10,000 people living here, design a sewage system to cope with 15,000. And then cheap flights came along and all of Northern Europe descended on Portugal for 3 months of the year because it was nice and warm and sunny. Suddenly you've got a population of 1 million pooing into a sewage system that can cope with 15,000 people. There's only one place it can go, and that's into the ground. So the groundwater for this interceptor sewer was around about pH 1 due to microbial influence effects on the groundwater, which means the concrete sewer had to be lined with epoxy inside and out, because that would just dissolve all the concrete we put in the ground. This again, piece of concrete, zoomed in, it's got limestone aggregate in. Limestone is calcium carbonate. Put acid on calcium carbonate, it dissolves. This particular process generates a bit of acid while it's treating nitrates. And so we etch the aggregate and we etch the cement, and basically we're not deliberately chucking acid in there, we're growing it as part of the process. Sulphate attack is the one that BRE Digest SD1 was designed for. And basically, if you stick concrete in the sea, there's chlorides, there's sulphates, there's living things. The one that attacks concrete specifically is sulphates. And we designed that out at the mixed stage, and it's easy to cope with. The thing on the right is the thaumasite problem that was discovered on the M5. Basically, that's a column supporting a bridge, and when they were doing an inspection of that column, they found they could put the hand through it. Now, Greek for thaumasite, thaumasite is Greek for to be surprised. The engineer who put his hand through the column was slightly surprised, in a polite version, because basically it turns it all to mush. Structurally, mush holding up the bridge immediately above your head while you're in a hole isn't the greatest thing to find. Alkali aggregate reaction. Alkali and the cement reacts with aggregate. Typically, it's silica is the aggregate that causes most problems, and that's called alkali-silica reaction. Something to note is glass is actually a reactive aggregate. If you put glass into concrete, it dissolves. I only mention that because in this wonderful world of sustainability, we all recycle. We all take bottles to the bottle bank or chuck them into a bucket outside and the council take them away. Most of the bottles you chuck away are going to be green glass or brown glass. We don't make green glass bottles in the UK, we don't make brown glass bottles in the UK, and we can't use green or brown glass when we're making architectural glass. Which means effectively, rather than it going into a big hole and being called landfill, it's being put into a big mound and called engineered fill. Completely different thing, but we accumulate around about 500,000 tonnes of green glass a year that we can't use for anything other than grinding into some kind of particle and using as fill. If you want to make alkali-silica reaction, take some glass, stick it into concrete. That's an example that the BRE did. Typically, alkali-silica reaction looks something like that, 3-leg crack. If you've got structural restraint, it can't crack like that. That gets pushed together. Which means that when you come along and you've got a post-tension structure, it cracks linearly. It's still alkali-silica reaction, but everybody got very confused because it didn't have 3 legs. The post-tensioning is basically compressing it, so it can't crack like that. And if we take a lump of it and send it off to a geologist, they get very excited because geologists are easily pleased. And they show us a slide that shows a piece of aggregate and some gel coming off it and cracks, and that's full of alkali-silica reaction gel. So it's easy enough to spot, it's easy enough to detect, it's easy enough to manage. A lot of the time we just deal with it in the mixed stage. Delayed Ettringite formation. Sounds like I've been a bit cleverer in the name, but Ettringite is something that happens when cement gets produced. And when you cast concrete, you get Ettringite. Delayed Ettringite formation is when the formation of Ettringite gets delayed. Normally this is because the mix has got too hot during the curing process. If it gets above 70 degrees C, you kind of muck up with the cement reactions a little, so it gets delayed. And you get cracks. And rather than looking 3-legged like ASR, they look a bit 4-legged. Again, if they're restrained, it looks kind of slightly different. The cracks can be quite large. This is passing the finger in the hole test, which is a common one used by engineers on site. But again, we can take a lump of it, send it off to a geologist, they get awfully excited, draw squares round blue things. That's basically concrete dyed blue to show up the problem. And you've got a load of this delayed Ettringite formation at depth, and then as it gets to the surface, it appears as a big crack. That's the chemical stuff. There's also physical attack. Salt recrystalisation. Salty stuff soaks in, dries out, you get a load of salt behind. More salty stuff soaks in, more water evaporates, leaves the salt behind. Eventually it just scales the surface off. Frost basically looks very similar. The water soaks in, freezes, gets bigger, slops the concrete off. Currently, it's kind of popular. We've got more frost attack than we used to have because we had a winter that was -10 to -14 for a long period of time. Occasionally people set fire to things under concrete bridges for some reason best known to themselves. They burn cars out and things burst into flames in the Channel Tunnel. Generally for concrete, I know it says if the temperature is greater than 300 degrees C, the strength's not affected. Actually, that should be less than 300 degrees C. At 300 degrees C, sometimes some concrete changes to pink. Doesn't always happen, so if you turn up at a fire damaged structure, knock a lump off, find it hasn't gone pink, it doesn't mean it's not got that hot. To be honest, if you get asked to turn up at a concrete structure that's had fire damage, it's had fire damage because that's why somebody's paying you to go. And concrete, despite it being hard and lovely and wonderful, it will wear away. That's a seawall in the Middle East suffering from salt recrystalisation. It's about 3 years old. Ambient temperature is about 40 degrees. The sea is slightly saltier over there than it is over here because it's 40 degrees and it's constantly evaporating. And we know it's not the reinforcement that's corrosion that's causing the problem because, to be honest, we can see all the reinforcement and it's not that corroded and the concrete's still going on behind it. The cover is that slightly darker browny stuff compared to the sand on the beach. It takes about 3 years for that to happen. Fire damage, break off lump, go, oh look, it's gone pink. But to be honest, most of the time when the concrete structure is degraded sufficiently to affect the strength, the concrete's fallen off. So then you're looking at what's gone onto the steel as well. Typically we consider concrete to be hard and very robust and lasts forever, and if there's something wrong with it, it's because they've cast it wrong. But give yourself long enough, everything can be worn away. That's a cast iron bollard in Wigan, at the top of a flight of locks. Everybody who's been through that lock on the Leeds-Liverpool Canal for the past 200 years has put a rope round that bollard, and the rope has rubbed on that bollard for 200 years. And as soon as you get a little notch, it starts finding its own way into that little notch each time a boat goes up and down. And yeah, it doesn't get used much now, but 200 years ago it was working flat out. And eventually the ropes wear away the cast iron. Soft stuff wears away hard stuff. And water can wear away concrete. This is a spillway in Afghanistan. And basically, all of that is exposed reinforcement. Next bay along, again, that wasn't designed to be that shape. This is before we turned up, as you can tell by the safety hurt and sandals approach to life. There was a hole down in this bit that we wanted them to investigate, so we said chuck a pole down. Couldn't find a pole, so they chucked an Afghan. He's actually laughing his face off. He really is, because you can zoom in on the picture. He's swinging his legs around, and the report from site was he couldn't find anything to put his feet on, so it's probably quite a big hole. That's important site feedback. Here you see some of the local aggregate that you basically have to use to make concrete. So we turn up, we give them all PPE, so they're now much safer because they've got a hard hat on and wellies and overalls, and we try and produce a repair spec. In this case, the client wanted the repair to be best quality. It's a bank-funded project. We want it to be repaired to the best standards we can. It's like, well, great. We'd love to use a proper concrete repair mortar that's been certificated in accordance with the European standards. But it's in Afghanistan and they haven't got anything. So it's going to be a case of accepting what they've got and working out a way of getting it to work. And it works perfectly well, but you can't just waltz in and say, right, we need to do this and this and this, because the skills and the equipment and the materials might not actually be available. Mechanical damage. It's surprising how often people drive into bridges. It really is. More commonly, people drive into parapets. For the structural engineers amongst you, this is what happens when a car hits a relatively young parapet. This is a 1990s car park in the days when we realised that basically parapets are there not to stop people from walking off the edge, but to stop idiots from driving off the edge. The BMW that hit that suffered slightly more than the parapet did. In the 60s, we didn't have that same approach. We thought parapets were there to stop the wind blowing through and give you some kind of edge protection, so that when a relatively modern car hits a relatively old parapet, these planks are basically secured to the columns with 4 bolts. So it's not that hard to drive straight through them. We looked after this particular car park for 6 or 7 years. And it's quite interesting because this happens every 2 years. And based on the number of spaces in the car park, that's basically 1 in 2 million cars that goes into this place makes its own exit. Now it's 40 quid for a morning to park there, so I can understand why, but if you're going to do it, don't do it on the 5th floor. You've a better chance of survival if you do it at a lower level. But yeah, it's a remarkably reproducible event, is people driving through the edge of car parks. All that's well and good, but most of the time what I deal with is rust. And to understand fundamentally why things rust, you need to look at where steel comes from. And where steel comes from, it all starts out with a big BANG! And the universe was created. Things were a bit chaotic for a while, but eventually we ended up on this lump of rock orbiting the sun 93 million miles away, and a chunk of this lump of rock is made out of brown mud. Structurally, brown mud, not brilliant. You can make piles out of it, but you're kind of limited when you want to make a skyscraper out of it. You can make pyramids out of it if it's hard enough. The Egyptians did that. But you can't get many shops in the bottom of a pyramid because most of the wall is structural. So somebody realised that brown mud was good if we could stick a load of energy into it. And as with anything, if you stick a load of energy into it, and in this case you make steel, it wants to lose the energy as quickly as it can. It wants to go back to its natural state. That's the way things work. How it gets there, here's we come on to the electrochemistry. Electrochemistry, combination of physics and chemistry. Physics in school was the stuff that didn't work. Chemistry is the stuff that didn't smell, that stank. So if you meet someone who claims to be an electrochemist, think doesn't work, smells, and you're probably not far off. Basically, take a piece of zinc and a piece of copper, stick them in salty water, nothing happens. The zinc sits there being zinc, the copper sits there being copper. But along with zinc having a density, a tensile strength, a coefficient of thermal expansion, when you stick it in salty water, it has a voltage. And zinc's voltage is -1. It's basically the Barry White of the voltage world. It's sitting there going, yeah, baby, right down here. Copper's voltage is +0.2, so it's up here. And copper is Jimmy Somerville. That's fine, they're quite happy like that. Merrily being zinc and merrily being copper. Connect them together with a wire, the zinc sits there going, hey baby, what's all this positive stuff? And the copper sitting there going, you're far too negative. So it starts chucking negative things at that to try and bring it down, and it starts accepting negative things from that to try and bring that up. The way it can throw negative things, the only negative thing it's got is an electron. The electrons, it can make that by dissolving. So it chucks electrons up there and dissolves into zinc ions in solution. That bit, electrochemically, is called an anode. The anode's the bit that loses metal. It's the one that's at a lower potential. The copper's the cathode. It's at a higher potential. It takes the electrons, reacts with oxygen and water, generates alkalinity, and you get electric current. That's what you get out of a battery. If you take the water away, you haven't got the potentials anymore, so you don't get corrosion. Dry things don't rust. That sounds all a bit, okay, I'll listen, but I'm not entirely convinced. This is a battery in a bucket on my desk with something called phenolphthalein in, and phenolphthalein goes pink when there's alkalinity being generated. So we drop that into water, and basically we can show that there was a big plume of pink came from that end, and then it starts heading towards that end. So we've got alkalinity being generated. Alkalinity is an ion, and the ion starts moving towards that end because that's covered in negative stuff, that's covered in positive stuff. So you get current flow through the solution. If I'd left it long enough, that end would go brown and rusty and dribbly, but to be honest, I get bored easily, so I didn't. So steel rust, it always will. How it gets there is anodes and cathodes. Steel in concrete, to be honest, if it always rusted, when Hennebeek came along with his great, wonderful idea for a reinforced concrete system, if it all started falling to bits after about 5 years, we'd be sat there going, that was a bit daft, wasn't it? Most of the time, steel in concrete doesn't rust because it gets this thing called a passive film on it. Yeah, we've stuck loads of energy into it, and yes, it doesn't really want to be steel, but we've given it a nice warm alkaline blanket where it sits there going, I can't be bothered changing back into rust, I'll just sit here merrily being steel. So it gets this nice thing called a passive film on it. Two problems. Salt. Salt punches holes in its nice warm blanket and makes it rust even though it's still alkaline. Atmospheric carbon dioxide is a bit acidic. So it soaks into concrete, that carbonates the concrete. Instead of the steel being in nice cosy alkaline concrete, it's in mildly neutral tap water, so it starts to corrode. The steel rusts, we lose reinforcement. Structurally, not great because we put the reinforcement in for a reason. Rust is bigger than steel most of the time, so bits fall off. The bits falling off is useful. It's not great if you get hit by a bit falling off, but it means that you've got an early warning sign that the steel is rusting. If bits didn't fall off, basically the steel would corrode and the structure would collapse and you would have no early warning of it. That would be bad. Carbonation is a typical example of a car park in Wolverhampton. Basically, the designer on this one specified 40mm cover. Good, won't carbonate. guaranteed, loads of cover, no problem. That parapet wall is 110 millimetres thick. It's got 2 layers of 12mm bars in each face. So if you've got 40 cover, 24mm for the outer layer of steel, that's 64 from one face, and then from the other face you've got 40 cover and 24, that's 64 from the other face, 128mm, fitted into a 110mm wall. The contractor basically did what he could to build it, so the cover's inadequate, because that was the only way to get the steel to fit in the wall that you've given him to do. There was a tendency to always blame contractors for there being a problem. It's not always the contractor's fault. Most of the time they're trying to do something that's relatively tricky in somewhere that's cold and wet with people shouting at them for why they haven't done it quicker. Concrete's all uniform, cover's all uniform, atmosphere's all uniform, so it all carbonates at about the same rate. Every bit of steel that's in a bit of concrete that's not alkaline anymore rusts, so the repair's quite extensive but quite easy to do. This is another car park structure. This one's in the northwest. Client knew they had a problem because bits were falling off, so they wrapped it in nets. Temporary measure, fine. Nothing wrong with that. Tiny problem, they didn't do anything with the nets. So after about 10 years, the steel carried on rusting because the nets didn't really stop that. And so rather than having bits of concrete hitting members of the public, you had nets full of concrete hitting members of the public. Not entirely the solution they were after. If you do something temporary, please bear in mind it's temporary and keep an eye on it and do something about it. Chlorides are slightly different. Basically, common problem in the UK, bridge beams under a joint leak, salty water gets on the crossbeam. All of that is full of salty water. But only about 10% of the steel's corroding, because that's what chlorides do. 100% of it's in chloride concrete, 10% of it's where the rust comes along. Similar kind of thing, this is up in Runcorn. There's a joint above that. Basically, it's leaked throughout its entire life. That bar, probably not doing much structurally. Nice spacing of the links for anyone who's doing modern designs. We've got little architectural features to make sure we got 10mm less cover than we needed. And so, the steel rust. Closer to this part of the world, M4 elevated. Basically, we got a motorway dynamically carrying people into the west end of London because they're posh and they need to be raised above the hoi polloi who deal with the A4. Immediately next to houses. We've got half joints. Half joints made it cheap to build. From my point of view, they're great because it means they leak, all the salty water collects on that shelf and you can't inspect it and you can't see what's going on. You just know that's probably going to be the worst bit of the structure. So from a concrete repair point of view, pain in the neck to fix. Great plan for consultants to sit there and scratch their heads and wonder what to do with it. On this one, somebody felt bad when they were building it. It's kind of like, well, okay, we've got to stick a motorway through the middle of a housing estate, but let's give them some credit. Let's put the drain pipes on the inside of the column because that way they won't have to look at the drain pipes. And I, for one, am much happier looking at a motorway if I can't see the drain pipes immediately out of the front side of my house. Drains block within about 3 months, so the concrete gets soaked from the inside out with chlorides. And we get bits falling off and we get anodes and cathodes forming. Up until about 10 years ago, everybody just thought it was in situ concrete because pre-stressed concrete gets built in a factory. It got built in a factory in the 60s and 70s, okay? In the 60s and 70s, for those of you who don't remember cars built in the 60s and 70s, just because they were built in a factory didn't mean you didn't want to waive your RAC membership because, to be honest, at some point you'd be on the hard shoulder of a motorway. For those of you too young to remember it, Top Gear did an episode highlighting the quality of British cars built in the 60s and 70s. It's built in a factory, improved quality assurance, so we're not going to have a corrosion problem. We've got higher strength steel. Now, higher strength steel stops rusting normally, and you get this thing called hydrogen embrittlement, of which I will talk a bit more later. Here's an example of a recent repair project where did a breakout on the pre-stressed beam and found there was a hammer in the beam that had been cast in at the factory. So yeah, better QA, but it turns out that basically we started using pre-stressed concrete en masse 20 years after we used reinforced concrete. And for everyone under the age of 40 out there, when you get to about 40 years old, suddenly that immortality of youth starts fading and you kind of get a bit spready and things start to ache. That's life. Happens to pre-stressed concrete as well as in situ. But that's all right because the Europeans have come up with a standard, including the British. We are in Europe after all. It's called BSEN 1504, and it's come up with a radical suggestion that step 1 is find out what's wrong with your structure before you fix it. That was highlighted by a study that was done about 10 years ago that demonstrated 95% of the attempts to repair concrete fail within 3 years. Because rather than actually finding out what's wrong with it, we see a bit of concrete falling off, turn up with some stuff in a bucket and slap it on the hole. That doesn't work. So we now find out what's wrong, then we design the repair, then we fix it, and we keep records and we maintain it, because everything only has a finite life. Nothing will last forever. 1504 is a bit of an odd thing. Part 1 is definitions. You'd think it was a good place to start if you wanted to know about it, but actually it's like reading a dictionary that's been written in English, German and French, and then translated into three languages and agreed by committees. So we got definitions in part 1. Products. Basically coat stuff, stick stuff in holes, glue stuff, inject stuff, anchor stuff and protect steel. That's in parts 2 to 7. They're really for the manufacturers. Principles is the one that tells you how to go about fixing things and what the investigation procedure should be. Contractors are covered under part 10, that says what QA you need to do on site. And then there's a bucket load of test methods that the likes of Sika have to get their product tested to before they can get a CE marking, which means they can sell it anywhere in Europe and it all has a similar basic level of quality. And part 8 is how the likes of Sika control their quality assurance. Don't go onto site, look up BSEN part 3 on repair materials, find out there's 200 things that it needs to be tested for and ask the contractor to test it for on site. All of that's covered by the CE marking. These are the principles in part 9. Starts off well. We need to stop the concrete from getting worse, so we'll stop stuff from going in. So protect it against ingress. Coat it, basically. But we need to control the moisture. How do we do that? Coat it. So why is it separate? Concrete restoration, okay. Put stuff in holes. Structural strengthening, straightforward enough. Physical resistance, not really much you can do to repair a structure to make it more resistant physically, other than put more structure around the outside of it. Resistance to chemicals, surely that's protection against ingress. So it kind of gets a bit loopy at times and a bit strange. But because there were 6 principles on fixing concrete, we're going to try and get to 6 on fixing steel, and we don't quite make it. Preserving or restoring passivity, that's basically taking chlorides out, removing carbonation. Increasing resistivity, the only way you can do that on a structure is dry it out. But we want it separate to moisture control because we're different, because we're dealing with the steel. Cathodic control. Remember the copper, oxygen and water generating alkalinity? That's the cathode. If you haven't got that, you don't get the anode. So if we can control that bit, we don't get corrosion. The only way you can control that is either dry it out, but not using moisture control, or starve it of oxygen. Bury it, basically. So if you write a spec saying I want my structure repaired to 1504 part 9, I can turn up and bury it. And that's within 1504 part 9. Because it starves it of oxygen, that's cathodic control. Cathodic protection I'll talk a bit about later, and we can control anodic in areas with things like inhibitors and protective coatings on the steel. First step, find out what's wrong. Is it rusting? Can you see any rust is the first step. Bear in mind the seawall from Dubai, it wasn't a rust problem, so you do need to know what you're looking at before you turn up and fix something. Easiest way, visual inspection, but we can also test. We can test for carbonation, we can test for chlorides, we can measure the cover to the reinforcement, we can actually measure potentials, these anodes and cathodes that form, we can measure them with a surface probe. Need to think a bit about the results, and we can quantify how much it needs repairing by hitting it with a hammer. That's a delamination survey. And we can either do this on the surface or we can do it at depth. So we can look at the face of a half joint that we can't see by drilling into it and collecting chlorides and collecting half cell potentials through depth. Is it rusting? That being, yeah, that's rusting. Structurally, is it doing anything? Well, no, to be honest, it's probably just applying load to that pipe. So is it worth fixing? Not unless that pipe really needs it. It's been designed out a long time ago. Carbonation testing, break off a lump of concrete, spray on something called phenolphthalein and measure the depth it goes pink. There we go, I've broken off a lump of concrete, I sprayed it with phenolphthalein, depth of carbonation is that simple. Phenolphthalein doesn't dissolve in water, it's a white crystal, so you dissolve it in alcohol, so it's a bit flammable. So you get a big cross on the COSH assessment saying, oh, hang on, you need to be careful with this, but we're only using it drops at a time rather than spraying gallons of it liberally. And one of the reasons we're not spraying gallons of it liberally around is because it's a laxative. It used to be the active ingredient in laxative chocolate bars at a concentration of 0.05%. The stuff we use is about 1% to 2%. It's not a comedy, ooh, I feel a bit unwell type laxative at 2%. It's a end up in casualty with a tube coming out your arm and a bucket underneath you. So always wear gloves and always wash your hands. Because of its toxicity and issues, there's some people would like it banned. The alternative is something that goes from greeny blue in alkaline concrete to bluey green in non-alkaline concrete. And as a site test, it's probably not that practical compared to clear pink. For chlorides, sorry, but we're going to have to drill a hole. And it's easy enough. Devilishly handsome engineer, drilling a hole in a whisper quiet drill. Basically, find the steel, because if you want to take a sample beyond the steel, you don't want to hit the steel. Drill a hole. Ignore the first 5 millimeters of the hole, and then you collect the dust at depth increments. Send the dust off to a lab for analysis, and you can measure cement content and sulphates. Sorry about that. Cover meter, use it to find the steel, write down the lowest number. Basically, you have to wave it about a bit. Hilti do one called a ferroscan. It logs as it goes, and you collect loads of data, and it can give you bar sizes, and it can give you spacing, and it can give you the variability of it. It's only an indication of bar sizes. Structurally, if it really, really matters that the bar's got to be a 30mm bar, break some out and measure it. Because the ferroscan's great, but it's give or take a bar size. Hilti also do an X scan, which is a ground penetrating radar handheld thing that can go in deeper than the ferroscan. Half cell potential, also known as reference electrodes, we measure the voltages. And because we know the voltages that are associated with corroding steel, we can work out where it's corroding. There is guidance on the readings, but they were based on 6 fridge decks in Florida and then universally adopted across the entire world. And they work most of the time, but some half cells don't work upside down. So if you're doing a soffit, make sure you've got one that works that way up. If you've got galvanised metal, it'll be kind of -900 because that's what zinc is. And because more negative indicates an anode, people get awfully excited when you get negative readings. It could just be there's a zinc post bolted into the concrete. Also, if you get down the bottom of a wall of an abutment, because there's not much oxygen kicking around on the buried stuff, the potential of the steel drops as you get down there. So it goes more negative anyway, even if it's not corroding. And what we're looking for is higher or lower. We're looking for Barry White and Jimmy Summerhill. And Barry White's the one that's corroding. Because we're just looking for higher or lower, we don't always need to connect to the steel. And there's my boss doing a half cell survey on the exterior of a tunnel. If you ever get to do that, important thing to find out before you drill the hole is how thick the tunnel wall is. Otherwise you're going to get wet. And there's him doing one on the surface of a deck in the days before adequate traffic management, where the health and safety approach involved keeping an eye out and being prepared to drop everything and run when you see something coming. This was during a tunnel closure, but the owners of the tunnel, they got 2 parallel tunnels, so they'll shut one, and the police will occasionally use it to drive up and down for a laugh, just to keep you on your toes. Hammer survey. Hit the concrete with a small hammer and write down where it sounds hollow. Small hammer is important, not for any particular inspection or repair reason, but because you're going to be doing that for the next 8 hours. And your natural tendency is to do the big hammer, because I want to look like Thor on site, including shiny breastplate and flowing locks. That's who I model my hero. But you're better off with a little one, because a little one, you'll be able to do it for more than 10 minutes without hurting. Sometimes it sounds hollow when it isn't. Sometimes it doesn't sound hollow when it is. So when it comes to actually repairing it, there will be some variability between what I have marked out as needing repair and what actually needs repairing. It's a fact of life, and as long as you've got a proper bill of quantities, you can measure it and work it out. That's concrete. Steel, basically, whether you stick it on concrete or not, when it corrodes, you get anodes and cathodes forming on it. You get little Barry Whites and little Jimmy Summerhills all over the surface. If we take this lump of steel, stick it in the ground, bury it for a while, we dig it up, that side looks basically rusty. Everybody thinks of that as corroding. But if you grit blast it, you find you've got bits where the metal's gone and bits where the metal hasn't got. And you've also got a little sad face down here. So you've got anodes and cathodes forming on the surface of the structure. It's not just me saying it, it happens, look. There's a couple of different types of corrosion that are worth mentioning. General corrosion, basically the anodes and cathodes wander about the surface. So you get a fairly uniform attack. You don't get many holes forming until the metal's completely gone, but you do lose quite a bit of section. So structurally, the fact that there isn't a hole in it doesn't necessarily get you off the fact you've lost 2 millimetres off the perimeter of your beam, because that can be a significant amount of metal. Because that's the type of corrosion that's been kicking around since we've been putting steel in things, there are typical rates available for most metal and environments. So you've got steel sheet piling corrosion rates if you put the steel sheet pile in the sea or in the river or in the ground. Don't always work because they are typical rates and there are occasional exceptions. How you deal with general corrosion, you keep the water out. And that's what a paint's for, just to keep the water off so you haven't got anodes and cathodes forming. Or you design out poor details that you can't inspect and are designed to collect water and debris and then lead to premature failure. For example, this particular car park, built in the last 10 years, we've got a channel. And the channel has been put that way up so that it collects water and debris and guaranteed to make it rust. And then we've bolted cladding to that face of it so we can't actually inspect that face. And we've got a crevice forming there and a crevice where that's attached. So we don't do that even though this is 10 years old. If they'd have stuck that the other way up, totally different kettle of fish. Much better from a corrosion point of view. Easy to manage. Easiest time to deal with it is in the design stage. Here's an ancient old pipe that's basically rusting. How you deal with that? Coat it. You'll come across something called pitting. Pitting is a geometric thing. It basically means its depth is bigger than the size of it. It's hole forming. And it's very localised, so you get holes. If you own a pipeline or a ship, holes matter. If you own a structure, most of the time, a hole in a steel beam, don't matter. Commonest cause is chlorides. And we're on an island surrounded by a big blue wobbly thing that's packed with chlorides, and we also chuck millions of tonnes of salt on the roads. And once initiated, they can carry on without any external influence. They can just get worse and worse and worse and worse and worse. How we deal with it? Same way we deal with general corrosion. We paint it. But we might make pitting where we get holes in the coating if there's salt kicking around. There you go. Pitting. Basically, that bit's not really corroding, that bit's corroding. In this case, pitting, we've got a hole. This was a pipe that was coated perfectly acceptably in a factory, and then they used steel chains to drop it into place on site, which removed all the coating locally, which means you've got corrosion site formed. Crevice corrosion. Little gaps mean you get crevices. Crevices mean you've got more oxygen out here than you have at the bottom of the crevice. Sometimes just debris forming can give you a difference in oxygen. You get differential amounts of oxygen and you get lots of intense corrosion in a very small area, so you lose section loss in a very localised area. Way to deal with it? Well, don't have crevices. Try and avoid them. If you're welding something, don't do a hit and miss weld with gaps to accumulate stuff and have small gaps, or fill them in. There you go, that's where you usually get a crevice at a bolted connection, just where you don't want it, which means all the corrosion that you're getting is concentrated there, which means that can pull out. Bimetallic corrosion, bi to metallic metals. If we connect zinc to copper, zinc's an anode, copper's a cathode, the electrical connection's there and we've got an electrolyte. That's just water. If we've got a big cathode and a small anode, the thing that governs how quick it corrodes is the amount of oxygen kicking around. The amount of oxygen that can be consumed at the cathode. So if you've got a big one of them, it can consume lots of oxygen, which means the anode can corrode as fast as it possibly can. If you've got a big anode and a small cathode, the small cathode can't deal with all the electrons that the anode wants to chuck at it, so the whole thing slows down. Small voltage difference is better than a big voltage difference. If you connect carbon to aluminium, you've got 1.5 volts. Duracell used to slag ordinary zinc carbon batteries off. That's a piece of carbon and a piece of zinc. That's how you get a 1.5 volt. That's a bicycle frame. A £4,000 bicycle frame made of carbon fibre with an aluminium seat post in it. So we've got about 1.5 volts in there, and that collects water. And the aluminium corrodes, and as the aluminium corrodes, it splits his £4,000 bicycle frame. He did take it up with the manufacturers, who weren't the most helpful and basically said, Well, you didn't follow the maintenance procedures. Oh, what are they? Not telling you. What are you saying? You shouldn't have got it wet. It's like, hang on. I should ride a bicycle but not get it wet in the northwest of England. That's not going to happen. One of the things that's becoming increasingly popular and increasingly worrying is something called stress corrosion cracking, or hydrogen-induced stress cracking, or hydrogen embrittlement, or any of those wonderful things. If you've got the right tensile stress and the right material and the right medium, you don't get normal corrosion. You get a tiny pit developing and then it snaps. That's bad. No warning, no obvious corrosion, snap, fail. As we get stronger and stronger steels, that's the world we're heading into. Just because the bolt isn't loaded like that, if you cut threads on the bolt, that's put stresses in locally. So that can give you the stress even though you don't think there's stress there. If you've welded it, that can give you the stress even though you don't think there's stress there. How we deal with it? Well, the easiest thing to do is don't pick a stupid grade of steel. Don't put that particular grade of steel in that environment. But if you have to, then you can coat it. But coatings break down with time and need reapplying. Here's a bolt. And basically, it's stress corrosion cracked and fell into a swimming pool underneath it. The owners of the swimming pool shut the balcony because they thought people were throwing things in the swimming pool, but actually it was the bolts falling out the roof. Not great if you're swimming along. That's a tank made of precast concrete panels. That one should actually look like that one. Basically, tilt-up construction, fold all them into place, shove a tendon through, pull it really tight. When it fails, that's what happens. How much warning do you get? Well, none that the site noticed. What happened? One of them full of poo emptied itself fairly quickly. Nobody died, but that's kind of good. But by the time this happened, there were thousands of these things built all across the UK, and every water company who'd built one went, oh, hang on. Mildly worrying. So it can happen, and it happens. In this case, we had high-strength steel tendons, and basically they got water on them, and they corroded and they snapped. But when they snap with no warning. There's no ductility, it just goes ping and fails. Anyone who deals with fatigue, there's a little side arm that the corrosion engineers throw at you called corrosion fatigue. Cyclic stress, corrosive environment. Cyclic stress gives you fatigue, corrosive environment gives you corrosion. It's kind of quite difficult to distinguish from plain fatigue, but there is one subtle difference. There's no stress limit. Normally, if you're not sticking something above a stress limit, fatigue doesn't happen for steel. Aluminium's not the same, it doesn't have a stress limit, but for steel, as long as you don't put it into that region, it's not going to fatigue. But because corrosion gives you little notches and little holes and little ductility problems and little stress raisers, locally you end up sticking it over that stress. How we deal with it? Coat it. Anything that we can do to deal with fatigue resistance also helps, so we can put the surface into compression by shot peening it or carburizing it or nitriding it. And that's an example of something that basically corrosion fatigued off. It's a fan casing, and that's where the failure happened before it ripped itself to pieces. Bugs good. NCE had a wonderful article, early 90s, about steel-eating bugs causing havoc in ports. They don't actually need to physically consume the steel because, as I showed on the sewage works before, they can change the environment quite significantly from something that was relatively benign to concrete to something that's pH 1 and eats through 10 millimetres of concrete. And the same thing can happen on steel. You can get little biofilms forming and you get multiple interactions, which means instead of having 0.1 millimetre a year loss of section, you've got 1 millimetre a year loss of section. It kind of changes your design for the sheet piling slightly. That's caused by biofilms, and we can get massive corrosion rates. That's a picture I showed before of a sewage treatment works. That's a super duplex stainless steel pump. 10 millimetre wall thickness, been in service for 6 months with a hole in it due to bugs. Don't happen everywhere. Everywhere you look for them by giving them the right type of food. So it's like looking to see if you've got a stray dog by throwing a pile of burgers in your back garden. You basically suddenly find, yes, you've got a stray dog, so that must have been the problem. Well, no, you've just chucked a lot of food down and attracted a lot of stray dogs. To stop rust, a couple of choices. One, use something that doesn't rust. Aluminium doesn't corrode. generally, unless you put alkalinity on it, but you've got fatigue problems. Gold doesn't corrode. Can't make a plane out of it because it's too heavy and it won't take off. So we end up using steel that we structurally understand quite nicely and we coat it. Or we can galvanise it, or we can use something called cathodic protection, or we can use corrosion inhibitors. I mentioned passive films for steel and concrete. Stainless steels basically do the same thing but in the atmosphere. There are lots and lots and lots and lots and lots of grades of stainless steel. If you just stick on a drawing that you're going to use stainless steel, the contractor will do what the contractor does. It is his job to find the cheapest way of meeting what you've asked for. So he will get a load of teaspoons, form them into something structural, and well, there you go, there's stainless steel. There's lots of different grades. There's a perception that there is something called marine grade stainless steel. There isn't. Marine grade typically means 316. Occasionally people think 316L is better than 316. It's not. The L means it's got low carbon in it, so it's easier to weld. Which if you're a welder is better, but it doesn't mean it's any more corrosion resistant. There's loads of different finishes and they affect how it's performed. If you get the right grade and the right finish and you build it properly, you get corrosion resistance. It can still go rust coloured. It can still rust. So there's a whole art to dealing with stainless steel. It needs a bit of thought. Coatings are the same. You can't just say paint it and expect it to last 15 years. You need to get the right surface. It needs to be clean enough and it needs to be rough enough. Normally that's where abrasive blasting comes in. Surface prep grades quoted as SA mean we are going to abrasive blast this. ST means we're going to mechanically prep this. You need the right coating. And if we paint it and we can see it and it's above ground, that's easy enough. If we can't inspect it, then that's where cathodic protection comes from, because we can protect the steel pipeline that's buried in the ground by sticking a different anode on it. Some coatings can coat with moisture, some can't. Cementitious coatings on concrete are great because you get the concrete wet to apply the coating. And that's a damn sight easier in the UK than getting the concrete dry to apply the coating. Epoxy coatings on concrete can coat with a bit of moisture. Urethanes on concrete, some can coat, some can't. Some turn into expanding foam as soon as you turn it on. Minor problem. A couple of different types of coatings. If it's chemically cured and you add part A to part B and you add too much part A, you end up with leftover part A after it's gone off and a horrible sticky mess. If you don't add enough part A, you end up with leftover part B when it's gone off and a horrible sticky mess. So you can't muck around with the proportions. If it's a catalytic cure coating, add part A to part B. More catalyst means it goes off quicker, which means you can get winter grades. You can get winter grades of the chemical cure as well, but for catalyst, more catalyst means it goes off quicker. Doesn't mean you can do it on site. You can't open a tin and a half of part A, bung it in, expect it to work like it would do normally. Doesn't work like that, but that's basically how catalytic coatings work. Solvented coatings is the way we used to do it. Basically solid stuff floating in something that evaporates. Paint it, stir it thoroughly because otherwise all the solid stuff's sunk to the bottom of the tin. Paint it on the steel, the solventy stuff evaporates and the stuff that's left forms a hard protective surface. We don't like solvents anymore. They're bad for the environment, so we take them out of paint and we put them into hand gel. It's just a completely different thing. There are lots of things that can go wrong with coatings. If you want an in-depth study of all of them, you need to be a paint inspector. If you never want to have to worry about any of them, you need to employ a paint inspector on any of your coating jobs. They are very useful things to have. Favourites: spotting the difference between crocodiling or alligatoring, ropiness. Holidays is paint to speak for, a hole in the coating. Grinning through means you can see the stuff that you've painted shining through from the old stuff. I had a hole that was painted maroon and I painted it something pale and it took about 7 coats before I got rid of the grinning through issues. Basically, most of them are it's falling off or it's cracked. Get a paint inspector. Main quality assurance measure for coatings: measure the thickness that it's gone. Check the surface prep before they apply the thickness, because there's no point checking it after they've applied the coating. And if the surface prep right and the thickness has gone properly, then it'll work. Easiest time to do that is when the paint is still wet, because if they haven't got the thickness on when it's wet, they can stick more on. If it's too dry, when you measure the thickness, you can use magnetic thickness gauges, work great. But there's not a lot you can do about it with some coatings. You can't just overcoat them with more to get more on. We can also measure adhesion. That involves sticking something onto the paint and then pulling it off, and you get the paint to fail and you write down the number. Occasionally you get into, if the contract has gone really horrible, you occasionally then get into strange conversations with a client where you need to repair the bit that you've just adhesion tested. But how do you know the bit that you've used to repair it has the right adhesion value? So you do a pull-off test on the bit that you've just put on to repair the bit that you've just done a pull-off test on, and it can get very, very strange if the contract's gone horribly wrong. Another way of doing an adhesion test is basically slash the paint with a Stanley knife and stick some duct tape on it. It's called the St Andrews cross test. It's slightly more controlled than I suggested there. And we can check for holes using a spark test or a wet sponge holiday detector, holiday being hole. That's paint. Galvanising, in the same way there's lots of different types of stainless steel, there's quite a few different types of galvanising. And basically zinc corrodes slowly. And also when you get a chip in the zinc's going to be an anode and locally protect the steel. Electroplate gives you about 5 to 25 microns of zinc. Iodizing or sheridizing, basically you stick a little bit in a tumble dryer full of zinc powder and you get 15 microns of zinc on it. Hot dip, you get 20 to 200 microns. Don't sit there, look at that 200 and go, right, every spec I write from now on is saying I'm going to have 200 microns of zinc on everything. Because how much zinc you can actually physically get on something depends on the size of the thing you're actually zinc plating. If you hot dipped bolts, it wouldn't work because all the threads would be full of zinc and there'd be no zinc on the shank. So bolts are spun galvanised. It's thinner, but it's good enough. It's the best we can do. You can also thermal spray zinc and get sometimes more than 200 microns on, but it depends on what you're doing and where you're doing it. Now for steel in concrete, basically when it gets full of chlorides, 10% of the steel corrodes, so 10% of the steel gets rust on it, so 10% of the concrete falls off. Historically, you come along, tell someone you want that repairing, they knock off a loose, repair it. So that gets repaired. Technically, that's now steel in uncontaminated concrete, so that's actually quite a good cathode. All the stuff around it is still full of chlorides, so it's a good anode, which means it come along and it rusts next to the bit you've just repaired. Where cathodic protection comes into the game for concrete, all that chloride concrete we can leave behind. M4 elevated, we don't need to remove the piers and replace them at a cost of 5 million quid. We can CP them at a cost of 200 to 300,000, depending on access and traffic management and all those fun. So all the chloride contaminated concrete can remain, which saves propping and access. It's not me being clever that costs money, it's actually physically getting to the work site and doing the work and supporting the structure while you're doing the work. So if you can save that, you save yourself a bucket load of cash. We also save materials and we save carbon, embodied energy and all that good stuff. So it's the right thing to do sustainably, but also it works out cheaper, which is entirely the reason it's done, not because it's good sustainability. Two versions, impressed current, you get a 6 volt power supply. Galvanic, you use something that's an anode to steel in concrete, zinc typically. That is galvanically protecting that. For impressed current, that's a piece of titanium. There's a wire coming off the titanium to a 6 volt battery, another wire coming off there to a piece of steel that's in there, and it's generating alkalinity around the bit of steel. And the current's flowing through the solution from there to there. That's impressed current. For equations, basically steel corroding Fe is going to Fe2 plus and 2E minus. Those two electrons are reacting with oxygen and water and generating alkalinity. We turn up, we stick an anode on the surface and we ram electrons into the steel. That goes away, so it stops rusting. All we're left with is this alkalinity. So we generate alkalinity on the surface, and if it's corroding because it's turned acid, carbonation, we can do that for a bit. It's called realkalization. That's covered in positive things because that's how it chucks electrons out. Because that's covered in positive things and chlorides are negative, they start heading over there towards the positive things to balance the charge out. That's how current's carried in solution. That's called electrochemical chloride extraction. Not done much, but can be done. And we can also move water around under the presence of an electric field due to electrochemical osmosis. The standards for CP that have been kicking around, that one's been around 15 years now, that one's been around coming up to 10, and that covers the people that are doing it, the designers, the installers, the people taking any kind of CP measurements. All the contractors have got well on board with this, And so people doing CP on site are actually trained and competent. The Highways Agency have advice note and the Concrete Society have guidance on it. And we can use it to protect any embedded metal of any kind of type of metal. We can get very long service lives. We need impressed current to do that, and you need to keep an eye on it to make sure nobody's turned the power off. And it cuts down on the extent of repair. Doesn't work through air gaps, so we can't CP a lamppost above ground because electricity through air is called lightning. We need to worry about stray current, but that's a design issue and is fairly simply dealt with. And sometimes we've built something that we can't CP. Inhibitors, basically mystic goop, clear, colourless, painted on, soaks in, stops the rust. It sounds like it's ridiculous, it sounds like it's too good to be true, but it does work, and lots of things have inhibitors in. If you ever used to fix anything on your car that was built in a factory in the 60s and 70s, the bit that you got to replace it was wrapped in brown paper. That brown paper contained an inhibitor to stop it rusting on the shelf. This is Forskrag Mine in the Lake District. It was owned by the National Trust. It was repaired in 2004, and it being a heritage property, they wanted it fixing, but not looking like it's been fixed. So we can't fix the steel by painting it, because then it wouldn't look rusty. So what we've done is put an inhibitive wax on that. It's clear, it's see-through. What you can see is not the colour of the wax, it's the colour of the steel before we coated it. And on the embedded columns that were there and there, we've used Seeker's corrosion inhibitor to soak in and deal with those parts. Fundamentally, there is a perception that things don't fall down. And largely they don't, but occasionally they do. Williamsburg Bridge, fantastic huge bridge with a really cheap budget, which turned out to be complete gibberish. Costs went through the roof, program went through the floor. I'm sure anybody working in construction is completely unfamiliar with these scenarios. In order to save money, it's a dirty grey suspension bridge. In order to save money, they decided not to galvanise the individual wires that make the main suspension cables up. Now, as cost-cutting measures go, that was a fundamentally stupid thing to do. And as a result, the main suspension cables were breaking within 10 years. Individual wires were failing. There's about 8,000 of them in a main cable, so one or two falling out the bottom ain't great. But if it's happening in 10 years' time, you know you've got a structure that's suffering. In 1987, the local authority who look after it were presented with a report that basically said there's a 5% chance of it failing, and failing involves 6,000 vehicles ending up in the river. As a local authority engineer, when this lands on your desk, you're not going to sleep well that night. I mentioned the 1 in 2 million before for cars driving out of that particular car park. 5% probability of failure? Not really that kind of acceptable, even if we design everything on a 95% confidence limit. You wouldn't want a 1 in 20 chance of a bridge dropping, really. If you look at probability analysis, if you ever head down that route, at some point somebody's going to ask, well, okay, can we accept a 1 in a million failure? Can we accept a 1 in a billion failure? And the answer is, don't know. Fortunately, in this case, it turned out there was a problem with the finite element modelling they did. There was a maths error, and actually it wasn't anything like that. But that's the Williamsburg Bridge. They're the main cables they save money on by not galvanising. Closer to home, Piper's Row, lift slab car park in Wolverhampton. A lift slab car park fell down during demolition, so everyone went, phew, that was lucky. Any more kicking around? Yes. Problem. Start doing some assessment, start doing some analysis. Keep the car park open because we want money from the car park. The designers, the inspectors, the assessors did a load of tests, identified that it would have problems and it would need propping. The props were in the car park, in storage, the night it collapsed and was still being used as a car park. It's a difficult sell that it's going to fall down. But at some point, you need to make that sell. You may find yourself in a position where you have to say that, look, I know it hasn't fallen down yet, but it's going to fall down and I can't tell you when. That's what it ended up looking like. There was a car parked in it, and there are rumours that when the owner complained to the owners of the car park, they pointed at the sign saying, we accept no responsibility for any loss or damage. Bit harsh. But it's happening all over the place. America's just better at telling people. Richest nation in the Western world and all that. Leo Frigo Bridge, didn't make the news over here. One of the piles corroded through under one of the pile caps and the bridge ended up looking like that overnight. That pier dropped 2 foot. Where they found out about it? Basically, people driving over the bridge rang the police and said, I came over here last night and I'm sure it was a lot smoother than this. Is it all right? So they end up going down, doing an investigation, and yeah, it's 2 foot lower. What do we do? Well, to be honest, replacing the piles is a tricky operation. So it does happen, and of course, there are bigger examples of it, and again, they're still in the States. And again, this was being repaired at the time. It's the I-35 collapse, and as a result of this, they did a big study showing how many bridges are suffering in the States. And they're substandard, so they're code failures, which means they don't meet what we expect of a bridge now. Doesn't mean they're going to fall down now, doesn't mean they're going to last 100 years. If you go into America on holiday, there is a website that points out where the substandard bridges are, so all you need to do is avoid them, and you'll be fine. Basically, things to remember. Number 1, steel rusts. That's what it wants to do. And we can stop it. Easiest time to stop it, design stage. Then we're looking at paint or cathodic protection or inhibitors or concrete. Concrete's great, but it cracks. It gets old, it gets damaged. Steel rusts, so it needs repair. And in order to repair it, we find out what's wrong with it. And then we fix it. We don't just rush out and gob stuff over the holes because somebody said it's great. And if you do it that way around, you can do a durable repair. It's all part of asset management, but fundamentally, bottom line is things will fall down. That's basically it for me.